Dr. Tammy leads Lawrence Livermore National Laboratory's Inertial Fusion Energy Initiative, and I will refer to IFE a couple times. We love our acronyms in DOE, so I apologize, but otherwise it's a mouthful. Where she directs experiments aimed at achieving fusion ignition at the National Ignition Facility. Dr. Ma works with universities and other institutions to advance the use of the world's highest intensity lasers to research into matter, astrophysics, fusion, and other subjects. With the IFE initiative, she helps guide foundational fusion energy studies at Livermore and in the wider community to support DOE's drive to commercialize fusion energy. Dr. Ma has helped build the high energy density science and fusion communities, including establishing the IFE Virtual Collaboratory to encourage connections between private and public fusion programs. Among her many other activities, she serves on DOE's Fusion Energy Sciences Advisory Committee, and in 2020 helped author a long-range plan for U.S. efforts in this area. Dr. Ma is an active communicator, providing congressional and executive branch briefs and testimony, appearing regularly in popular media, volunteering at science fairs, and speaking to groups that encourage women to participate in science. She made numerous appearances to communicate the importance of fusion and NIF's ignition achievement, including with CBS TV's 60 Minutes, and can be found on multiple YouTube videos. Dr. Ma received the 2013 Presidential Early Career Award for Science and Engineering, a 2018 DOE Early Career Research Award, and was recently named recipient of the Krell Institute's 2023 Coronis Award in Leadership, Community Building, and Communication. Fellow of the American Physical Society, Dr. Ma earned her Bachelor of Science degree in Aerospace Engineering from Caltech and her Master's of Science and PhD from the University of California, San Diego. It's my pleasure to welcome Tammy.
Thank you, Jeff. I promise the YouTube videos was not why I became a physicist. All right, so today I get the pleasure of sharing with you this talk, Creating a Star on Earth, Ignition and a Fusion Energy Future. I do get the honor today of giving this talk, but really I don't get to take much of the credit. This work does build on decades of research by an incredible team across Livermore and the wider DOE community. And some of our many collaborators are shown here on the right. So our Earth faces an array of threats to its environmental and social balance. Some of them are shown here. These are just some of the threats we have to worry about on a day-to-day basis. Nuclear warfare, atmospheric and underground nuclear testing, energy-related greenhouse gas production, technology disruption, industrial processing, greenhouse gas production. Why did I pick these threats? Well, fusion energy, and specifically fusion ignition on the NIF, has an impact on each of these areas, and we're going to talk through that today. What is fusion? It is the reaction that powers the sun, and the one that we're primarily interested in is deuterium and tritium, which are isotopes of hydrogen, heavy hydrogen, which we're going to fuse by getting them very hot, very dense, and what comes out on the other side is a helium nucleus and a neutron. And the idea behind fusion is that our products, that helium and the neutron, are going to weigh a little bit less than our deuterium and tritium originally did. Of course, we stick that into Einstein's equation. That differential in mass becomes the m, multiplied by c, speed of light squared, huge amounts of energy out. And so the Q of fusion, the exothermic energy released for fusion, is a huge number, 3.3 times 10^11 joules per gram. That means for every gram of fusion fuel, we're releasing about the energy that's in 100 barrels of oil. So the energy density in fusion is enormous. Okay. There are at least 3 ways to achieve nuclear fusion, and some of them are more familiar to you than others. They are gravitational confinement, like in the sun, magnetic confinement, and inertial confinement. So gravitational confinement, the sun, of course, is this huge mass that can hold itself together long enough for fusion to happen, right? Each of these are going to reside in a very different density temperature space. With the sun, gravitational confinement, we're very dense, 10 to the 4 times solid. KeV temperatures, so relatively low temperatures for very long confinement times, 10 to the 5th years is the amount of time it takes radiation to escape from the center of the sun to the outside. Magnetic confinement, primarily tokamaks, stellarators, using magnetic fields to hold plasmas together, very low density, very hot, 10 keV, hold together for seconds. The type of fusion we're going to be talking about today is inertial confinement, primarily with lasers, very dense, very hot, and because you're dense and you're hot, your pressure is enormous, right? So we can only hold our plasmas together for on the order of tens of picoseconds. So inertial confinement fusion, like Jeff said, we like our acronyms, ICF, can be achieved by using high-power lasers to drive a spherical implosion. There are two main approaches to fusion. Let's talk about direct drive first. That's the one on the bottom. That's where we're going to use lasers to directly shine on a fuel capsule that contains our deuterium and tritium. We're going to take that laser energy to compress the capsule and heat it at the same time. And the pros there are that you're going to have higher coupling efficiency. You're directly taking laser energy, turning that into your compressional energy, and you're going to have reduced laser plasma interaction effects because you're taking laser energy to drive this implosion. The other approach is called indirect drive. That's the one on top. Rather than having your lasers shine directly on your fuel capsule, we're going to shine into a canister, which we call a Hohlraum. It's a German word for empty space, empty room. The lasers hit the inside wall of that Hohlraum, which is typically gold, depleted uranium, something high up the periodic table, high Z, right? The lasers are going to generate an energetic flux of X-rays, and we use those X-rays to compress that fuel capsule. The pros with indirect drive are there's relaxed beam uniformity. It's a little less important exactly where you point the lasers, how uniform each of the laser focal spots are. And then with that, because we're using now X-rays to do the compression, we're going to have reduced hydrodynamic instabilities. In either case, as soon as you deliver energy to your capsule, the reaction becomes the same. What's going to happen is we are going to start ablating the outside surface of that capsule very, very quickly. Then, by conservation of momentum, the rest of the fuel compresses inward by blow-off, in a rocket-like reaction. Your fuel core, if you do it right, will reach 20 times the density of lead and 100 million degrees Celsius, that 10 keV. You're going to spark a little burn right in the center of that DT fuel, and then it's going to burn through the rest. And if you do it right, you have ignition, more energy out than you put in with the lasers. And this work that I'm talking about today, like I mentioned, is built on decades of innovation, in fact, 6 decades. The first concept of ICF was born in the late 1950s, and the laser was invented right around 1960. And as legend goes, just a few days after the laser was invented, that man on the top left, John Knuckles, who later became one of the directors of Lawrence Livermore, came up with the idea of using lasers to actually drive fusion, right? That is the bold, audacious thinking that marks our national lab system, marks DOE. How can you imagine that a laser, a couple of photons at that time, it was nothing, not even laser pointers like we have today. How could you have the idea that you could actually use lasers to make miniature stars? That's crazy, right? That's the legend of John Knuckles. And after that, that launched a series of lasers at Livermore, bigger and bigger, 9 in fact, until in 1992, we had the key decision to start construction, or to start building the National Ignition Facility, the NIF. We completed construction of the NIF in about 2010. Thank you to DOE for working with us and taking this enormous leap to make this giant facility possible. And then we started experiments in 2010, steadily for over a decade until recently in 2022 when we got that shot ignition, more energy out than we put in with the lasers. Now, the history of Livermore, the history of the NIF and laser fusion overlaps very nicely with the overall mission space of the DOE and the National Nuclear Security Administration. You can see that in 1992 was the end of what we called underground nuclear tests, right? We had the Comprehensive Test Ban Treaty where we decided, you know what, guys, let's make a pact around the world. We're not going to do underground nuclear tests anymore. But guess what? Many countries, including the US, still had nuclear weapons. So how do we ensure the safety, security, and effectiveness of our nuclear stockpile in the absence of testing? Well, we turned to what we call science-based stockpile stewardship. That was one of several justifications for why we built the NIF, because we can now generate these very high energy density conditions with this type of laser facility that would allow us to do the science we needed to underpin the reliability of our stockpile. So reaching ignition really is the culmination of decades of passion, hard work and learning. So let me introduce you to the NIF. We are at Lawrence Livermore, which is about 50 miles east of San Francisco. Many of you will probably do your practicum at Livermore. Hopefully at some point you do get to come visit. I would love to give you a tour. We are building our own miniature sun, and this is what it looks like from the outside. NIF is the world's largest and most energetic laser, which enables the study of extreme conditions for high energy density science. As you can see, it's the size of 3 football fields side by side, 10 stories tall. It's actually 192 separate laser beams. Each one alone is one of the most energetic in the world. Combined, we have a total energy of 2.05 megajoules and a power of 500 terawatts. Now, I'll note that that is 1,000 times the power of the entire US electrical grid. But of course, your lights do not flicker at home when we take a shot, which happens about once a day, because what is power? Energy per unit time, right? So it's a huge amount of energy that we're going to compress in just a few nanoseconds, on the order of 25 nanoseconds or less. For you laser nerds out there, this is frequency tripled neodymium glass, which means the wavelength that we shoot into the target chamber is 351 nanometers. It is UV. Okay. And if I take the roof off of the chamber to give you, the facility to give you a look inside, you can see that most of the facility is actually taken up by optics, because what we're going to do is use just a series of very, very large meter-scaled optics to amplify that laser up 1,000,000 billion times from its seed. And the laser is going to bounce back and forth all around before it is focused down on this target chamber at the end of the facility, which is 10 meters. 30 feet in diameter. And right in the center of this enormous target chamber is going to be our little target. So here is the actual hole rod, and here is the fuel pellet held up to a human eye to give you a sense of scale. It's about 2 millimeters in diameter. And so we utilize the NIF in 4 main ways to ensure confidence in the current and future stockpile. Those 4 ways are: the first, we support stockpile decisions for the current and future stockpile. What we mean by that is we are able to do experiments on the NIF to kind of study the microphysics inside what we have nuclear weapons. Microphysics, right? We're not making new weapons, but what we do with that understanding of physics is we feed it into our very high fidelity computational codes, the same HED codes that we use to underpin our stockpile. A very important thing is the training of the next generation of nuclear weapons scientists and engineers. Actually, this is my graduate student, Elizabeth Grace. And what we do is all of the science that we do on the NIF in support of ignition is openly published. It is a part of deterrence. It is part of stockpile stewardship to show how good we are at the science. That's actually part of our deterrence, and that's what hopefully many of you will be doing too. And then advancing our understanding of weapons science. This is just an example of our material strength experimental platform. On the NIF, we are able to study plutonium, we're able to study titanium, all different types of materials to understand how they react under high pressures. And then expanding our conditions to reach more extreme conditions, i.e. ignition. Because what ignition means is a burning plasma that feeds on itself, that can actually create energy on its own without having more energy added. So that is a very unique platform to actually have. When I talk about ICF, what we're doing is bringing star power to Earth. But whereas the sun is 1,000,000 miles across, the suns that we're going to generate in the lab are on the order of 2/1000ths of an inch, about half the diameter of a human hair. Going one step deeper, again, the NIF uses a laser-driven hole-rom to compress a fuel pellet of deuterium and tritium to achieve those conditions for ignition. That hole-rom that I talked about is a cylindrical cavity that serves as an X-ray oven. So that little canister has 2 holes on either end. We're going to bring the lasers in to shine on the inside wall. Each laser has to hit a very precise spot to generate a symmetric flux of X-rays. So just like your oven at home, you're using heat to kind of uniformly distributed bake a pie, right? What we're trying to do is cook our little pellet here as symmetrically as possible. So the X-ray flux that we're going to generate is on the order of 300 eV Planckian or so. So very, very hot. The capsule sits right in the middle. And what we actually do is we're going to build the whole ROM in 2 halves, spread a very thin membrane across the 2 sides, and clamp that capsule right in the middle. The capsule, again, is 2 millimeters. You can see here there's actually a little fill tube that sticks into the side of that capsule. It's like a little straw. That way we can actually fill the pellet with deuterium tritium before the shot. And then this canister, the whole ROM, is about 1 centimeter in length, 0.5 centimeter in diameter. If we zoom in now and have a look at the capsule, this is just a pie diagram cut out of the capsule. It is typically plastic or HDC, high density carbon, essentially diamond, with many different layers. And so we'll actually dope different layers of the shell with things that are higher Z, like silicon or tantalum. The idea is we need to actually protect the fuel that sits on the inside, which takes the form of a DT gas because it's compressible, but then we also have to grow a cryogenic DT layer, an ice layer. So just like water ice, but just pure DT. And we have to grow that layer so that we can actually cram enough fuel inside our capsule such that you would have propagating burn, enough fuel that you can actually generate more energy out than you put in. And the trick of inertial confinement fusion really is to turn 100 million atmospheres of pressure, and via spherical convergence, right? You turn that into 300 billion. So you take that capsule that was 2 millimeters in diameter, and you're now going to compress down to about half the diameter of a human hair, 50 microns or so. And then you're going to take this kinetic energy of compression, and if you do it right, you can efficiently turn that into heat. Now, this is really difficult because you need to stay as symmetric as possible the entire time you're compressing to efficiently turn that kinetic energy into heat, right? Anything that deviates from round, you're wasting the kinetic energy. And the reason this is so difficult is if you can imagine trying to squeeze a balloon in between your hands, right? Everywhere it can, that balloon's going to squeeze back out. You're wasting that energy. And so that's why we need so many lasers. That's why we actually use a whole ROM. And so this is a very complex process that you can imagine. We have to rely on numerical simulation to capture the multi-fidelity, multi-physics of ICF. There's about 10,000 different physics parameters that we can change on every single experiment. The size of the capsule, the materials you use, exactly where the lasers point, the pulse shape, the power output is a function of time that we put into the laser. So you can see here, this is an example of the laser pulse, total power versus time, in terawatts versus nanoseconds. Each of these bumps that you see in the laser power, as we turn up the power, that drives another shock into the capsule to help us with the compression. And this simulation here is a hydrodynamic, radiation hydrodynamic simulation with Hydra. And you can see here, these are the laser beams coming in. They interact with the ablator, they interact with the whole ROM wall. The wall itself, over those nanoseconds, doesn't stay still. It turns into a plasma and expands. It can actually impede the laser coming in at later time. Here's the shell as it is ablating and then at the same time compressing. And you can see this is a very dynamically evolving situation that you absolutely have to rely on simulations to try to understand. I'm going to play you a little video now to show you how it all comes together. We start out in the NIF control room. This is where I spend a lot of my time when it is my experiments.
Ready for shot. Starting countdown for shot on my mark. 3, 2, 1, mark. Clock is running. 5, 4, 3, 2, 1, shot.
So first, the laser is going to be born in the master oscillator room. It is born at a nanojoule level. This is 1,000 times less energy than a typical laser pointer. It is a fiber laser. The laser gets shaped in time and split 48 ways going into the preamplifier module, where it's going to bounce around close to 100 times, getting amplified up to the millijoule level, so now about a laser pointer. Each beam gets split another 4 ways and then gets sent into the main amplifier, where it's going to bounce back and forth across our enormous facility 4 times, getting amplified up to the kilojoule level. So in total, again, 1 million billion times for each laser beam. So now we're going to follow one of the laser beams, and each beam is actually about 40 by 40 centimeters. Again, not a little laser pointer. And the reason the laser is so big is because we actually have to spread that laser energy out over the optics as it is traveling through so as not to damage the optics itself. Now, all 192 laser beams are going to go down to the end of the facility, go towards that target chamber, that blue ball. Half the beams get sent up, half get sent down. They're going to frequency convert from infrared to green to UV. This helps with the laser plasma interaction effects. And they have synced up now. At this point, they're all incident on that tiny target that sits right in the center. Half the laser beams coming in through the top, half through the bottom, radiating that inside wall to generate that 300 eV Planckian-like X-ray flux. And those X-rays start now ablating the outside surface of the capsule. The shell starts blowing off at about 300 kilometers per second. The rest of the fuel squeezes inward, and if we do it right, ignition. More energy out than we put in with the lasers. And so on December 5th of last year, 2022, fusion ignition was finally realized at the National Ignition Facility. And about a week later, the Department of Energy hosted us for a media panel in Forrestal. And it was a really exciting day for science. There's not many days when science makes the top fold of the New York Times, and this was one of them. Okay. And so the fact that we reached ignition, it's a goal that's been laid out since the beginning of the Stockpile Stewardship Program and opens new capabilities for us to sustain our nuclear deterrent and sets the basis for inertial fusion energy. So this plot of fusion yield over time, ooh, these are small labels, sorry. I don't have a mentor anymore that like points out these mistakes. So if you can read, this should start around 2010 through to today. This is fusion yield in megajoules. Each of these is one of our deuterium-tritium experiments that we've done on the NIF. So over about 10 years, that was about 200 experiments, which if you think about it, is really not that many. Of course, each of these experiments is accompanied by a bunch of other experiments where we don't put DT in the fuel. We don't want to create those neutrons. 200 experiments over 10 years. This pink line shows the max laser energy that was available, meaning when we first turned on the NIF, we didn't turn it on full bore, right? And we tried to improve the laser over time. And you can see that in 2021, 2022, we started seeing major improvements. And I'll talk through how we got to this point where we finally had a shot that exceeded the amount of laser energy we delivered. How did we know we achieved ignition in December? Right. What ignition actually does is it triggers very rapid increases in the temperature, size, and mass of the fusion plasma, which then contribute to increased fusion yield. So why this is such a big deal, and I alluded to it earlier, is because for everything else in the universe, right, if you want to heat something, you first have to deliver a certain amount of energy and convert it into heat. And you're never able to get more heat out than you put in. For the very first time, in a controlled laboratory setting, we were able to generate something, a burning plasma, and let it go, and then it kept feeding back on itself. That's a really, really big achievement. What we're going to show here is a series of 3 shots, March 2021, August 2021, and then finally that December shot. Here's a plot of temperature versus those 3 shots. You can see the temperature jumping up quite a lot. Because you get hotter, the plasma actually expands, so the radius actually increased 1.6x over about a year and a half. The mass increased by 4 times. And then this series of 3 images shows neutron images. This is from a neutron detector that we worked with Los Alamos with. We can actually image what the plasma looks like because it is generating neutrons in that hotspot. And then in March 2021, this neutron hotspot is pretty small. It's relatively cool. And then by December, you can see that we have something this is a very well-behaved hotspot. If you look at some of our earlier scientific papers, you'll see it's all like cronky looking. But this is like a Gaussian type hotspot. It's very round. This is a very, very well-behaved hotspot. And then we saw with target game over time what that actually means. And so what do we actually do, right, to get this great result? Well, to ignite the target, on that shot was the first time that we had turned up the laser to over 2 megajoules, 2.05 megajoules, 440 terawatts. This is an 8% increase compared to where we were the year before. And so this gives you an idea of how close we have actually been for quite a while now. If you just turn up the laser energy a little bit more, it gives you a lot more bandwidth to actually, a lot more flexibility in your actual platform. And so on December 5th, our laser happened to deliver really, really well. And what I mean by that is you have 192 separate laser beams. You need to make sure they all get there at exactly the same time. They are all shaped exactly the way you want. They all have good power accuracy and power balance between 192 beams. And so what this plot actually shows is you can barely see underneath the red and blue lines is a black line, which is what we request of the laser. The red and blue is what actually gets delivered. And so for anybody that's an experimental physicist, this is amazing. The NIF laser typically delivers within 50 microns pointing, 30 picoseconds timing, and a few % of power accuracy to give us those conditions that we need for ignition. Our ignition shots also require some of the most precisely engineered targets made by our target fabrication team. I've shown you some schematics of the target already. This is what the actual built target looks like. It's a little more complex than what I had before. There's probably 8 different temperature sensors on this target to hold different components at different temperatures. This arm that we put on this enormous boom to push into the target chamber, that boom is over 5 meters, right, in length. So you can imagine the stability there. But each of these little golf ball ridges, what that actually does is help just in case one of our lasers should miss point. If a laser hits the edge of the target instead of going into the hole realm, the laser that bounces back doesn't go directly up the same beam path and blow itself up. And then these are components of the target. Here is the actual capsule. This is a diamond nanocrystalline capsule. We have to grow the crystal to be nanocrystalline. It is 2 millimeters in diameter and smooth to 10 nanometers. You can imagine, when you fabricate anything, there's going to be little bumps and divots on that surface, right? We have to polish and make sure it is smooth to 10 nanometers. And then here is an X-ray of the capsule before we actually take a shot. As I mentioned, we have to grow a very precise ice layer on the inside. That ice layer itself also has to be very smooth. If there are grooves in the ice, if the crystalline that we grow is not uniform, we actually have to remelt. So it takes us about a week to grow a good enough ice layer before we can take a shot. And that's one of the things that actually limits our shot rate as well. And so our target improvements have not only focused on reducing material and engineering defects. The plot on the left shows the improvement in capsule quality from 2018 to 2021. We were able to reduce pits and voids not only on the surface of the capsule, but within the material itself by 2 orders of magnitude over the past couple of years. And then that fill tube that I mentioned to you, that is the straw that we use to push the DT in as a liquid before we grow that ice layer. We started out initially with something that was 50 microns fill tube, again, half the diameter of a human hair. We saw that even that small thickness of fill tube was causing a perturbation, a hydrodynamic instability that would grow into our capsule as it was being compressed. And so over several years, we tried to bring down the size of the fill tube from 10 to 5 to 2 microns is what we shot last December. And with that, you get an enormous reduction in the perturbation of the surface area. So it's not only these advances in both target quality, but also our ability to actually characterize. Because we take all of this information from the characterization of the target, and we do put it into pre-shot simulations, and post-shot simulations, so that we're able to actually capture the full physics of all of these effects on the performance. And besides those improvements, over the past couple of years, we've brought up dozens of diagnostics that are applied to each experiment to improve understanding. Currently on the NIF, we have over 100 different diagnostic instruments measuring everything you can imagine: X-rays, neutrons, gamma rays, optical light coming out, so that we can reconstruct the performance of every single shot. And for us, this is a great place where we get to work with other national labs, work with universities. We've gotten several students through PhDs because they are able to bring up diagnostic instruments to work with us on the NIF. And then, of course, I would be remiss if I didn't mention AI and ML. What we do with AI and ML is that we combine simulations and data to improve our understanding of the previous experiments and aid in optimizing future designs. So what we're able to do is, we do try to do those high-fidelity simulations I mentioned for a set of shots. We can't do them for every single one, because even on our supercomputers at Livermore, they typically take 2 to 3 months to be that high fidelity, right? So you have to carefully pick which experiments you actually fully model. Instead, we get to rely on 1D, 2D simulations and apply machine learning as well, because we're running tens of thousands, hundreds of thousands ensemble simulations where we can then look for trends and apply machine learning, right? So what we can do is explore vast assigned spaces for optimal performance. We can predict what we might expect to see. So here's a plot of yield versus ion temperature that we might expect from a set of implosions on the NIF. We do our experiment. It never turns out like we expect. So we learn, update our models for next design iteration. In the meantime, try to quantify the discrepancy, look for explanations for the data, part of our hypotheses, and then we feed back. On our December shot, based on our AI ML loop, we did predict a 50% probability of ignition. Now, of course, that wasn't the first time we had predicted 50% probability, but it actually worked that time. OK, so what is our next step on the NIF? We're going to continue to exploit ignition for stewardship while speeding up our paths to tens of megajoule yields and high gain. What we want to emphasize is NIF has not yet reached its full potential. It is a facility that's now 20 years old. Some of you guys are probably about 20 years old. You haven't reached your full potential, but but it is an aging facility. So we're working with Congress over the next few years to do a sustainment plan and then upgrade potentially to 3 megajoules or 600 terawatts. And then our plan is over the next few years to get to tens of megajoules of yield by like 2028, and then beyond that push to hundreds of megajoules of yield. Now, the same fusion plasmas that we create for national security applications can also be exploited to be the basis of a clean power source via inertial fusion energy, IFE, like Jeff mentioned. Ignition on the NIF basically establishes the scientific feasibility of using this for an energy source. And you can see that when we announced ignition, there was a lot of excitement in the media. We on the panel, we were very careful to make sure that we were talking about the stockpile stewardship mission for what NIF is funded to do. But everybody made the leap to fusion energy, one little wave of energy on the grid, right? And so, going forward, we are definitely going to explore this, but developing an economically attractive approach to fusion energy is a grand scientific and engineering challenge. And I say economically attractive because I have no doubt that we will get to fusion energy. The question is, can it compete with our other energy sources? And fusion energy is actually attractive for many reasons, even though it is incredibly difficult right now. First of all, it is safe. As I've talked through, you've seen how difficult fusion is, right? You first have to deliver a sizable energy source to make fusion actually happen. If you ever want to stop a fusion reaction, you cut off that initial energy source. It's different from fission, where you do have runaway. It is entirely carbon-free. There's no carbon anywhere in the equation. It is sustainable. We know how to obtain the fusion fuel that we need without damaging the environment. In fact, 1 in every 10,000 particles of seawater is deuterium. Deuterium is naturally occurring. Tritium we know how to breed from lithium. It's envisioned that fusion power plants would be able to meet base load. They'd be hundreds of megawatt or gigawatt scale power plants, similar to coal power plants of today. And it's a reliable energy source, right? You don't need the sun to shine or the wind to blow. You can also modulate your power output as needed by your population at the time. There's no geologic storage, there's no high-level nuclear waste associated with fusion, and energy security. So if we can demonstrate fusion to be a viable energy source, no longer will we be reliant on foreign oil imports. And if energy becomes so abundant, right, it completely changes our paradigm with energy. We stop having to go to wars to get that energy resource, right? So IFE power plants will consist of 4 main parts. You might have the engine that looks a little bit like NIF, but on the NIF right now, we've achieved a gain of 1.5, right? 3 units out for 2 units in. In order to make fusion work for a power plant, you would need gains of 50 to 100. So there's still a lot of work to do. And some of you said you were, starting in plasma physics and fusion. I'm very excited because we need help. But also, we would have to shoot about 10 times a second at 10 hertz instead of what we do on the NIF today, which is shot every 4 to 8 hours. So you need a target factory to deliver those targets, preferably at low cost. You need a driver that's efficient. You need a fusion chamber with walls that can withstand the irradiation. And you need to convert that energy into electricity with something like a steam plant. But as I've alluded to, the NIF is a scientific exploration facility, right? We're not a power plant. We're just exploring things for the first time. It's very different from what would be needed for an IFE power plant. That single shot versus 10 hertz, in addition to all of these subsystems that we have to develop, including tritium processing, remote maintenance, et cetera. But the good news is, even though there are enormous challenges we have to overcome, a number of promising technologies that we need are already making steady progress. Okay. So it is now time to broaden the nation's fusion energy portfolio to include both magnetic fusion and inertial fusion. So everything we've done on the NIF to date has been funded by the National Nuclear Security Administration for the Stockpile Stewardship Mission, not for energy. However, within the Office of Science, and Asmarie has left, that's too bad, we have fusion energy sciences, but they've been putting most of their money into magnetic fusion over the last decade. So we do like to point out this plot, which is a comparison of all fusion experiments to date. This is the Lawson criterion, which is how close you are to ignition, which is a parameter of density times confinement time, how long you hold the plasma together versus temperature. Most of these red points are magnetic tokamaks. These black points are the lasers, and NIF is the only one that has passed the ignition threshold. There's a couple of others like ITER and SPARC that are listed on here. Those are not completed yet to date. So we'll see how they actually do. So there's many advantages to inertial fusion energy. And basically, if we can have a balanced and diverse fusion portfolio in the US, this maximizes our potential pathways to success. And we have to build on the US's lead, right? We need to stay competitive. So last year, the White House held a summit to announce a bold decadal vision for commercial fusion energy. The whole country now is getting behind pushing towards fusion in a viable time frame where we can contribute to hopefully net zero and other goals. And so if we're going to make IFE happen, we're going to need a national plan, program, team, and sustained commitment. And to figure out what we need to do today, what you want to do is look ahead and say, if someday you want an economically viable commercial power plant, we have to roll back and figure out what should we be doing to make that happen. Well, if you take a step back, we want demonstration plants and pilot plants in the years 2030 to 2040. That means today we have to start technology maturation. That means publicly led hubs, government-funded hubs for component R&D, looking at pre-competitive technologies that can benefit everybody, leverage the existing facilities that we have because it takes so long to construct them, rely on public-private partnerships to help figure out what the designs for those power plants should be, and then start building dedicated inertial fusion energy facilities. And so our community is ready. We are getting all amped up. And in addition, there's been significant private investment into fusion startups in the past few years. And you've probably heard some of the news where there's all these companies popping up. This is a plot of funding in billions of dollars, again, over time. Blue is the Department of Energy funding, and green is the private venture capital funding that's been coming in. So you can see we're starting to get eclipsed by the private sector. This number should actually now be $6 billion into the private industry, but only about $200 million of that into inertial fusion. And this map shows where most of those private companies are. We still have a critical mass here in the US, but they are popping up around the world. And so, ignition does provide us with fresh impetus and the scientific foundation for inertial fusion energy. I don't want to say that this will be easy, and I don't want to give you a timeline, but the challenges are many, but the benefits outweigh the challenges. If we can make fusion work, this is energy and climate security for the US and scientific competitiveness. We do expect a bunch of spin-out technologies as well. And so, to make this happen, we need an inertial fusion program that leverages NIF as the world's only ignition platform, and then work with private companies to accelerate the path towards a fusion pilot plant. And we really want to see a partnership between all of DOE, bringing together all those different agencies and all of this expertise, because as you could see, we need technology development in all kinds of sectors. Yeah, I will finish, I promise. There it is, okay. So fusion ignition enhances our deterrence and offers a long-term vision for global climate and energy security. We've now demonstrated ignition, and what that does is open up a new set of conditions where we can do weapon studies, all kinds of cool astrophysics, passive fusion energy. But IFE, if we can make it happen, is a game-changing technology. It can provide abundant energy while helping to meet CO2 goals, bolster the US's science and technology leadership, security, and energy independence. However, it is a multi-decadal grand challenge endeavor. I expect to be employed for quite a while working on this challenge, and I hope many of you guys will come and join us. So the US is the leader in ICF, and we must capitalize on it to realize fusion energy for the world. Thank you.